Prove that magnetic dipole moment of a current loop is Pm equal Nia, where N is the number of turns of the coil, I is the current, and A is the area of cross section. In the diagram, A be the small a be the radius of a current loop or circular coil carrying current I. The current I flows through the circular coil of radius A. O be the center of this circular coil, and an axis is drawn, an axis which is perpendicular to the plane of the coil, that is the axis OP is drawn. The point P on the axis of the coil is at a distance x from the center O of the coil. X is the distance of the point P on the axis of the current loop. At the point P, magnetic field induction B acts along the axis and away from the current loop. The magnetic field induction at the point P on the axis of the current carrying circular coil is given by the magnetic field induction, that is the magnetic flux density, that is the magnetic flux density at the point P. Magnetic flux density at the point P on the axis of a current carrying circular coil is given by, at the point P on the axis of the circular coil, on the axis of a circular coil, the magnetic field induction, that is the magnetic flux density at the point P on the axis of a circular coil carrying current I, is given by B equal mu0 Ni A square divided by 2 under bracket a square plus x square whole to the power 3 by 2. Mu0 Ni small a square divided by 2 bracket opened a square plus x square or x square plus s square bracket close to the power 3 by 2. So we get B equal mu0 Ni A square 2 bracket open x square plus s square whole to the power 3 by 2, which is equation 1. And this magnetic field induction at the point P on the axis of a circular coil acts along the axis and away with respect to the coil. It acts along the axis, of the coil, and away with respect to the coil. It acts along the axis of the coil and away with respect to the coil. Again, we can assume a magnetic path. Now we can assume that if the point P is far away from the center of the coil, if the point P lies far away lies far away from the center of the coil. From the center of the coil. In the center of the coil, that means from the point 2 of the coil, comma, the distance of the point P from the center of the coil, that is x, will be much greater than the radius A. Then x will be much greater than small a. If you draw the diagram to explain this, this is the vertical circular coil, and we can draw the axis of the coil. Axis of the coil, which is far away from the coil. This is the axis which is at large distance from the coil. Here x is very large, means the distance is very large, means the point P lies far away from the center of the coil. A is the radius and current flows through the circular coil in this way. In this way, the distance x is much greater than the radius a. X is much greater than a. Point P, that means it is far away. Is far away from the coil. It is far away from the coil. This distance is very large. The distance of the point P from the coil is very large. In that case, magnetic field induction B will be acting along the axis and away with respect to the coil. B is the magnetic field induction at the point P, which acts along the axis and away with respect to the coil. And so now, if we use this relation, that is x much greater than a, that means neglecting a with respect to x, that means neglecting the radius of the coil a with respect to the distance x of the point P from the coil, we get neglecting a radius of the coil, that is a, with respect to the distance of the point P, that is with respect to x, we get the expression of magnetic field induction. Neglecting a with respect to x in the equation 1, that is in the expression of magnetic field induction B, we get B equal, B was what was the expression of magnetic field induction B? B equal mu 0 Ni square divided by Ni square, Ni a square divided by 2 under bracket a square plus x square whole to the power 3 by 2, where n is the number of turns of the coil and a is the radius, small a is the radius. Mu 0 Ni a square divided by 2 x square bracket closed whole to the power 3 by 2 to the power 3 by 2. Here, where a approximately equal to 0 with respect to x, that means assuming a as 0 with respect to x, equal mu 0 Ni a square equal mu 0 Ni a square, mu 0 Ni a square divided by 2x cube equal mu 0 by 4 pi. If we modify the expression, mu 0 by 2 pi Ni under bracket pi is square, pi into square of radius divided by x cube equal mu 0 by 4 pi 2 Ni a capital A divided by x cube, where a equal pi a square which is the area of cross section of the coil, which is the area of cross section of the coil. Area of cross section of the coil. Therefore, B equal mu 0 by 4 pi B equal mu 0 by 4 pi mu 0 divided by 4 pi 2 ni capital A divided by x cube. So B equal mu 0 by 4 pi 2 nia by x cube. This is the magnetic field induction at a point which lies far away from the center of the coil. This is equation 2. This is equation 2. Equation 2. B equal mu 0 by 4 pi 2 nia x cube. Now we can assume a magnetic bar having south pole and north pole, and dipole moment, magnetic dipole moment of this magnetic bar or magnetic dipole, that is Pm, acts from south pole to north pole. An axis is drawn. Axis is OP. X is the distance of the point P from the midpoint O of the magnetic dipole or magnetic bar. X is the distance of the point P from the midpoint of the magnet. And magnetic field induction at the point P due to the bar magnet is VAX, which acts along the axis and in the same direction of magnetic dipole moment Pm. Again, the magnetic field induction at the point P on the axial line of a magnetic bar or magnetic dipole. The magnetic field induction at the point P on the axis on the axial line of a bar magnet or magnetic dipole, bar magnet or magnetic dipole, is the magnetic field induction at the point P on the axial line of a bar magnet or magnetic dipole is, and on the diagram, this is the bar magnet having south pole and north pole. This is the bar magnet or magnetic dipole having south pole and north pole. And due to that bar magnet, magnetic field induction at P is BAX is equal to mu 0 by 4 pi 2 pm divided by x cube. Equation 3. And it should be long bar magnet, not only bar magnet, it should be long bar magnet or long magnetic dipole. So this is the expression of magnetic field induction. BAX equal mu 0 by 4 pi 2 pm by x cube. Equation 3, where pm is the magnetic dipole moment of the bar magnet. This is, we can draw a magnetic dipole or magnetic very long magnetic bar having north pole and south pole. O is the midpoint of this long magnetic bar. Magnetic dipole moment Pm acts from south pole to north pole, and this is what long magnetic bar or magnetic dipole. long bar magnet or dipole. Long bar magnet or dipole, and we can draw the axis up to the point P. X is the distance of the point P from the midpoint O of the bar magnet. At P, magnetic field induction, resultant magnetic field induction due to long bar magnet or magnetic dipole acts. P is the magnetic field induction at P due to the long bar magnet on the axial line. So here we can write also the magnetic field induction or flux density at the point P on the axial line of a long bar magnet or magnetic dipole. Axial line of a long bar magnet of the bar magnet or of the long bar magnet or magnetic dipole is given by long bar magnet or magnetic dipole is given by B equal mu 0 by 4 pi 2 pm divided by x cube. 2 pm divided by x cube. This is equation 3. B equal mu 0 by 4 pi 2 pm by x cube, which is equation 3. Equation 3. Comparing equation 2 and 3. Comparing equations 2 and 3. Both are the expression of magnetic field induction B. Comparing the equations 2 and 3, we get mu 0 by 4 pi 2 nia by x cube mu 0 divided by 4 pi 2 nia divided by x cube equal mu 0 by 4 pi 2 pm by x cube. Therefore, if we compare this left hand side and right hand side, we can write Pm is the magnetic dipole moment. Pm equal Nia, where N is the number of turns, I is the current flowing through the circular coil, and A is the area of cross section of the circular coil. Pm equal Nia. Pm equal Nia. So this is the magnetic dipole moment. This is the magnetic dipole moment. Magnetic dipole moment of current loop or circular coil. Current loop or circular coil carrying current I of area of cross section A, capital A, area of cross section A, capital A, and number of turns N, capital N. A is the area of cross section of the coil and N is the number of turns. Now we can draw the diagram of circular coil, current carrying circular coil here. vertical current carrying circular coil. One wire current will enter into the coil and flows away from the coil in this way. This is the circular coil. Current flows anti-clockwise from the phase observed from right hand side. So this is what rear view, and this is front view. Front end of the coil, and that was rear view or back face of back end of the coil. And here, with respect to right end or right face of the coil, current appears to flow anti-clockwise. That face of the coil behaves as magnetic north pole. If we observe the coil from right end, current appears to flow anti-clockwise, and that phase behaves as magnetic north pole. This phase acts as north pole, magnetic north pole, N pole. And if the same coil is observed from left end, at back face of the coil behaves as magnetic south pole, behaves as S pole, magnetic south pole. So same coil consists of south pole and north pole, south pole and north pole, and so it is called magnetic dipole. Current carrying circular coil behaves as a magnetic dipole having two poles, south pole and north pole. And we know that dipole moment acts from south pole to north pole. That means from back face to front face, from left hand end to the right hand end. And here dipole moment vector PM acts from south pole to north pole, means outwards. Area vector is also acting outwards, because dipole moment vector PM has the expression in I vector A. Vector PM has the expression in I vector A. That's why area vector is also acting outwards. Now we can explain that why does a current loop behave as magnetic dipole. Same coil is drawn here. Circular coil, through which current flows clockwise direction, from through one wire current flows into the circular coil, and through the other end of the wire, the current flows from the circular coil. Current flows clockwise, and that face of the coil behaves as south pole according to clock rule. This face of the coil behaves as magnetic south pole. On the right hand side, if the same coil is observed from back face, current will appear to flow anti-clockwise. Current will appear to flow anti-clockwise. Current enters and flows away from the coil. Current appears to flow anti-clockwise. According to clock rule, the phase through which current flows clockwise behaves as magnetic south pole. If the same coil is observed from back face, current will appear to flow anti-clockwise. That face of the coil behaves as north pole. So a coil has magnetic south pole if it is observed from one face, and the same coil has magnetic north pole if it is observed from back face. That's why the coil is called magnetic dipole, because it consists of two equal and opposite magnetic poles. And so you can say that a current Current loop can be regarded as a magnetic dipole. Can be regarded as a magnetic dipole. Current loop can be regarded as a magnetic dipole. Magnetic dipole, as if a current as if a current I flows through the coil clockwise, flows through the coil, flows through the coil, flows through the circular coil clockwise, comma, that face of the coil behaves as magnetic south pole. That face of the coil, that face of the coil behaves as behaves as a magnetic south pole. Also, the same coil, also the current will appear to flow. The current appears to flow anti-clockwise through the same coil. The current appears to flow through the same coil anti-clockwise anti-clockwise if it is observed from the other face of the coil. If it is observed from the other opposite face of the coil, or it is observed from the other face of the coil, face of the coil, and a magnetic north pole. A magnetic north pole is induced on that face of the coil, on that face of the coil. On that other face of the coil.